Robots that can adapt like natural animals. A paper in Nature that describes damage recovery in robots via the intelligent trial and error algorithm. How can we get robots like these to adapt to damage like natural animals? Before deployment, a robot uses a novel algorithm to autonomously create a map of different ways to behave and the value of each behavior. Here is a variety of entirely different ways to walk produced by this algorithm. Note that the behaviors are only tested in simulation at this point. The discovered behaviors create a map of the behavior performance space. The map shown was created with the Map Elites algorithm and contains the robot's intuitions about different ways to move and the predicted performance of each way of moving. Now see the undamaged robot controlled by a classic tripod gait. Note that the robot moves straight and at a speed of 0.25 meters per second. The robot has now become damaged. Let's see if it can still walk. Unfortunately, this robot, like most robots, no longer works if damaged. Because the pre-damaged behavior no longer works, the robot needs to adapt. The robot conducts a handful of experiments to determine a behavior that still works despite the damage. To do so, it combines Bayesian optimization with its intuitions about the behavior performance space provided by the map from the Map Elites algorithm. Here is the first gait from the map it tries. Each experiment updates the robot's understanding of which behaviors work and which do not. After the map is updated with this new information, a new type of behavior is tested by choosing a high-performing behavior from a different region of the map. The map is then updated based on that experiment, and the process repeats. Note that the map is getting more blue over time, meaning that the robot is learning that most of the performance predictions from simulation on the undamaged robot do not perform that well on the real damaged robot. In less than 40 seconds, the algorithm has discovered a gait that's nearly as effective as the original. Because the map predicts a better gait may still exist, the robot conducts one more test, but that prediction turns out to be wrong. The intelligent trial and error algorithm thus terminates, selecting the best gait found, which is nearly as fast and straight as the original. Watching the gait in slow motion reveals that it is dynamic and really seems natural. It almost looks like a wounded animal limping away. The gait is mostly straight and is 96% as fast as the original gait before damage. The same algorithm can work with many other robots. We tested it with a robotic arm. Like many robots in factories, the arm's job is to place an object into the appropriate bin. In this case, damage occurs when one of the motors becomes unresponsive. Once again, the damage prevents the robot from performing its job. The robot needs to adapt, so the same intelligent trial and error algorithm is launched. Here you can see multiple different behaviors being tested, the performance of those behaviors, measured as the distance to the target, and the map of predicted performance values being updated. In the upper right hand corner you can see how long the process takes, which is only a matter of seconds. In less than 20 seconds, without one of its motors working at all, the robot is able to adapt and complete its task. Our experiments verify that intelligent trial and error enables the legged robot to adapt to at least 6 different types of damage, including completely removing 2 legs, and 14 different types of damage to the robotic arm, including 2 motors being broken. When a piece of one of the legs of the hexapod breaks off, the classic tripod gait no longer works. Here is the result of intelligent trial and error after only 25 seconds. In this case, the damaged robot is even faster than the original. Now let's see what happens with the robotic arm if 2 of its motors don't work. The original behavior no longer performs the task, as expected. But after 28 seconds, the arm adapts and is able to drop the ball in the basket. For more information and additional videos, please see our paper in Nature.